Hi, my name is Luc van Donkersgoed, and today I would like to talk to you about reaching peak event-driven architectures with DynamoDB Streams. I would like to start to go over a few event-driven design principles. And the first is to use services instead of custom code. So if there's a solution for which there is an AWS service available, use that service instead of trying to build the solution yourself. A common example is if you have a messaging requirement or a queue requirement, you use SQS instead of implementing your own queue service, because it is unlikely that you will be able to build a service that is as reliable and as durable as an AWS managed service. The second one is pretty common knowledge, is to use implement statelessness in functions, because a Lambda function might run once, or it might run 1,000 times concurrently, and every one of those executions needs to be able to run in isolation and at any time. Then there is the principle to prefer many shorter functions over fewer larger ones, and to build for on-demand data instead of batches. And today we will be paying specific attention to items 1 and 3, and we will see how DynamoDB Streams can help us achieve that. So to summarize these design principles, the core concept is to reduce the responsibilities of your functions. And that is really a key topic that we will be coming back to a few times today. And to help you understand why reducing the responsibilities of a function is so important, we will first look at a non-event-driven architecture. So in our library inventory system, there's a user and that calls an API gateway to reserve a book. The API gateway is backed by a Lambda function, and the Lambda function does a few things. First, it checks DynamoDB if your membership is valid. Then it checks if the book that you're trying to reserve is available. And then it places the reservation by putting an item in DynamoDB. Then it will call a backing API that actually starts the process of moving the book off a shelf and putting it somewhere where you can pick it up. And when that process has completed, the Lambda will use SES to send an email message to you confirming your reservation. But of course, there are a few problems with this design. And the first is latency, because this Lambda function has so many responsibilities, it takes a long time to process every one of those steps. And during that time, the user has to wait for a response, which is a bad user experience. The second one is fault tolerance, because if any step in this Lambda function fails, it has to start over. But there is no failure mechanism, so the only way to start over this process is if the user reserves the book again. And again, that's a bad user experience. And the third one is variability, because we have an external web service that might be fast most of the time, but it might be slow when there's network congestion or during peak hours. And that might mean that this entire Lambda function is slow as well. And again, that is variability, and that is bad user experience. So let's look at a few examples of event-driven architectures to see how we can improve the solution. And the first one involves SQS. So again, the Lambda function does what it has to do in DynamoDB. It checks if your membership is valid and if the book is available, and then it places the reservation. But instead of calling the backing API, it now puts a message on the SQS queue, and another Lambda will be triggered by that message, and that will fetch the reservation from DynamoDB, call the backing API, and then send the email. Now, because this function responds to the SQS queue, if it fails during this process, it will just return the message to the SQS queue and then try again at a later time. So there's fault tolerance. Also, this Lambda function can just execute the bare minimum of what it needs to do and then respond to the user, which is pretty consistent because there won't be much delay between Lambda and DynamoDB and SQS. And it's pretty lightweight, so the Lambda function will respond to the user pretty quickly. So that's a better user experience than in the previous design. Now this solution works fine if you only have one backing system, so this one Lambda function. But if you have multiple backing processes, you might want to use fan out using a simple notification service. So in this case, the Lambda function triggers SNS. SNS then fans out and sends a message to one Lambda function and another Lambda function, but also places the same message on the SQS queue, which then triggers the same Lambda we saw on the previous slide. Now this is a good solution when all of these Lambda functions are within your responsibility domain. So you control this Lambda function, you control this Lambda function as well, and the SQS queue and this Lambda. So you know all the processes that are there, and you know how to perform updates on them. But if you have more downstream processors that you do not control, for example, other teams processing this message, or you do not know which processes will be handling these events in the future, a better solution might be to involve EventBridge. This is, again, the same process where you reserve the book, but now instead of triggering SNS, we just put a message on the EventBridge message bus. And the message bus has all these messages, and we have other Lambda functions and other processes that can filter the message bus for the events that are important to these functions, and they respond to them and them only. And this is really a great solution for multiple accounts and multiple teams, because any team or any account that is configured to do so can read from this bus and process the messages without this Lambda function having to know about all the downstream processes. Now these services, the EventBridge and SNS and SQS, are considered the integration layer of a serverless and event-driven architecture. So these integrate the business logic layer, the lambdas and the step functions, by decoupling them and passing messages in the way that we just discussed. But now let us zoom in on this Lambda function. So we discussed that it has multiple responsibilities. It checks your subscription and it places the order, and then it sends a message onto EventBridge. But this has a number of implications, because if you want to change the integration layer, for example, change SNS into EventBridge, you now have to update the function that is there to reserve the book. So the responsibility of this function is to reserve a book, but now it also needs to know about the downstream process, whether it's SQS, SNS, or EventBridge. And that means that the function is more complex than it needs to do, than it needs to be, that you need to touch it more often than you might want to, and that it is slower than it could be because it has more responsibilities than the bare minimum. So let's see how we can improve on this architecture using DynamoDB Streams. So a quick introduction to DynamoDB Streams. It's actually pretty simple. We have a DynamoDB table, and there's a number of operations that you can do on it. You can create items, read items using query or scan, update items, and delete items. And whenever you do a mutation, so that's create, update, or delete, that can trigger an event on your event stream. And that event stream can send its events to a Kinesis data stream, a Lambda function, or both. You can also read directly from the stream with a custom application, but we'll leave that out of scope for today. Now, what's important to remember is that once you configure a DynamoDB stream, it will contain every mutation in the table. So if your stream and your database contains multiple objects, so you might have books, libraries, users, subscriptions, and more, then any mutation on any of those types and any of those objects will trigger an event in the event stream, and it will be sent to the event processor. Now, the DynamoDB stream can be configured in 4 ways. There's keys only, new image, old image, and new and old images. So let's take a quick look at what that looks like. If you configure your stream for keys only, and you perform an insert on your database. This is the event that will be sent to a Lambda function. It will have the event name insert. The stream view type is keys only, because that's how we configured it. And it will contain the primary key. So in this case, that consists of a partition key and a sort key of the item that was inserted. But you don't get any data about all the attributes or all the data that was part of the item that was just added to the database. The same when you do a modify, you get the event name modify, but you don't see all the attributes of the item that were actually modified. And again, when you remove the item, you get to see the keys of the item that was removed, but not the actual data that was removed. Now, if we configure our stream for new image, the insert looks a bit different. Now we still have the keys that identify the item that was inserted, but we also get all the attributes of the item under the new image key. So this was the item after it was inserted into the DynamoDB table. Now, when you do a modify, you get to see the attributes after the modification, but you don't get to see the attributes before the modification, so you can't actually tell what was changed. And when you do a remove, there's no new image because the image has been removed, so you again only get the keys. Now the inverse of that is of course old image. When you insert an item with a configuration of old image, it contains the keys, but there is no old image, so there's no data. When you do a modify, you get to see the data before it was modified, but you don't get to see the new data. And when you do remove, you get to see the item that was removed and all its attributes, because of course that was the image before it was removed. Now the final configuration is new and old image, and it is really the combination of the previous two. So you still get the keys. You also get to see the new image when you do an insert. When you do a modify, you get to see the old image and also the new image. So now you can actually tell which fields have been changed in this modify operation. And when you do a remove, you get to see the old image. Now it should be clear that new and old image is the most versatile mode, and it offers you all the data that you need in any kind of situation. Personally, I always configure my DynamoDB streams to use new and old images, but there are some use cases where you might want to use keys only instead, or maybe new image. And that is mostly in situations where your DynamoDB contains large items, maybe up to 400 kilobytes. And all of the data is part of your stream, and then you're paying for the data that you're using, and it might slow down the Lambda functions that you're using. And you might choose to use another solution than new and old images. So now that we've seen how DynamoDB streams work, let's take a look at what we can do with them. And first we'll take a look at the old architecture that involved SQS. And as we discussed earlier, the Lambda function will do a put item when you reserve a book, and the primary key is, or the partition key is reservation number this, and the reserved item is this ID, and the amount is 2. So this is put in DynamoDB, and in our old solution, a message would be put onto the SQS queue. Now in the new solution, we can remove SQS, and instead we have DynamoDB Stream, which contains this event, and the Lambda function can respond to that event and do everything that it needs to do. So it can call the backing API and send a message to SES. Now this already removes one component because the SQS component is no longer there, and less components is generally better. And it removes some custom code from this Lambda function because now it can really focus on what its responsibilities are, because it only needs to put the reservation into DynamoDB, and it doesn't need to worry about the propagation of that event at all, because that's picked up by DynamoDB Streams. But earlier I said every event in a DynamoDB table, every mutation will generate an event in DynamoDB Streams. So that means that if this DynamoDB table contains more types of items, so it doesn't only contain the books, but it contains the users and the libraries and their locations as well, then this Lambda function that is responsible for processing reservations will suddenly contain or receive many more updates than what it actually is built for. And you could build it in such a way that this Lambda processes all of those updates where applicable, but then this Lambda function contains many more responsibilities than the single responsibility that you actually wanted to have. So let's take a look at how we can solve that. Well, one thing you could do is have multiple DynamoDB processors on your DynamoDB stream. So that would look like this. Every event goes to all of these Lambda functions. This is not actually a nice solution because all of these Lambda functions would then receive all of the events, and early on in their process they could drop the events that they are not interested in, but still they would receive them and they would be triggered and they would count, for example, to your concurrency limit. So this is not the best solution and certainly not the most efficient solution. A better solution would be to have the Lambda, for example, the reserved book Lambda, put something on DynamoDB that generates an event on your DynamoDB stream, and that triggers a Lambda that converts that event into an EventBridge message that is put on the message bus. So this might be a message that says, hey, a user has been created, and this might be a message that says, hey, a book has been reserved. And because these Lambdas can apply filters, or there is a filter before the Lambda is triggered that filters only the relevant events, this Lambda will only be triggered in case of create user events. This Lambda will only be triggered in case of reserve books events. And this Lambda will only be triggered by create user events as well. And this is really the kind of architecture where every Lambda has a bare minimum of responsibilities, and their responsibilities are very clearly scoped and bounded. So this Lambda only processes the reserved book. This Lambda only converts DynamoDB stream events to EventBridge messages, and these Lambdas only do what they are responsible for. So at this point, we can say, well, let's update the image, the architecture, and say DynamoDB Streams is now part of our integration layer, because as you saw in the previous slides, it integrates multiple services together, and it takes that responsibility. So now let's look at a bit more advanced example and see how we can use DynamoDB Streams to optimize our single table designs. So a quick recap of single table designs. DynamoDB has no join statement, and there's a good reason for it. And the reason is performance. So if you look at older relational database designs, you would have a database with multiple tables, for example, a books table and an author table. And the book would contain an ID, the title, the publish date, and then reference by author ID to an author, and maybe the excerpt. And then the author would contain the name, the date of birth, and a biography. Now, if you would want to receive all of the books, including all of their authors and their bios, you would do a select everything from book and then left join the author on author ID. And then you would get a result in which the books and the authors have been combined. And this is really accessible and really easy to use, but it might perform very well in a small table. Maybe you have 1,000 books and 100 authors. But when that database scales and it grows into 1,000,000 books and maybe 100,000 authors, then this join statement might become very slow. And then you need to start to do query optimization and database performance optimizations. And that becomes really difficult to maintain, and it will cost you a lot of time. So to prevent this from happening in DynamoDB, the DynamoDB designers said, we will not have any feature that will not perform at scale. So any DynamoDB table should perform as well with 100 items in it as it should with 1,000,000 or even 1,000,000,000 items in it. And join statements have no place in that design. So we still need to query our data, and we still need, for example, to query our books with all their authors. But we don't have any join statements. So what DynamoDB states is that you should design your tables for the access patterns of your application. So let's take a look at what that means. We have the library inventory system, we still have the books and the authors, but before we design our table, we first determine the access patterns. And in our example, we have determined that there are two access patterns. One is we want to get all the books with their authors and their bios. And the second one is we want to get all the authors born in a specific year. Now let's take a look at how to design that DynamoDB table. We might have a partition key that contains the books and the authors, and we have a sort key that contains the type of the item. Then we have a global secondary index that has a composite key. The partition key is SK, and the sort key is GSI SK. Now, if we would want to get all the books with their authors and their bios, we could do a query on the GSI, where the SK matches book. And that would return all the book rows, and that would include the author, because that's included here. And it would also include the author bio, because it's here. Now, if you want to get all the authors born in a specific year and their bios, you would query again on the GSI. You would set the SK to author, and you would set the GSI SK to begins with 1926, and that would return all the authors born in 1926, including their bios. But you will see that the author bio has now been filled in for both the books and the author, so there's duplicated data. And this is really a concept that you do see in NoSQL designs, but you would never do in a relational database where every data is normalized. So the reason we've duplicated this data is that if we wouldn't have done that, and we would want to get all the books with their authors and their bios, you would first query all the books and you would get the authors, but then you would have to query every author individually to get their bio, which means that if there's 1,000,000 books, instead of one single query, you now have 1,000,001 queries, and that's not performant at all. And by replicating this data, you really have a very optimized database. So there's duplicate data, but now we need to manage that duplicate data, because what happens when you update the author in this system? You perform an update item, and you might say the author Harper Lee, we have a new bio. And what the result in this table would be that the actual author that we just updated has the updated bio, but now the book written by this author does not have that updated bio. So, well, a simple solution to make sure that that book also has a updated bio would be first to update the author, then query all the books for that author, and then update the bios for all of those books. But then we're getting back to the subject of responsibilities, because now this Lambda that has the function update author suddenly also has the responsibilities to update the books, which is not what it was written for. So the responsibilities become unclear, and there's a lot more to maintain. So let's look at how we can use DynamoDB Streams to improve on this. So in this case, we have DynamoDB Streams, and as we discussed before, we're sending every event to EventBridge. Now, when we update the author, the DynamoDB stream will contain a modify event that will be put on the EventBridge message bus, and then this Lambda will trigger on the fact that there was a modify of an author and perform post-processing. And the post-processing is to query all the books that are written by the author that was just updated, the Harper Lee, and then update those books accordingly. And now all the functions have their bare minimum of responsibilities again. This Lambda only updates the author, this Lambda only puts messages on the EventBridge message bus, and this Lambda is only responsible for post-processing update authors, and they will all only be triggered when actually called. So you could say that in this design, the book written by Harper Lee has a relation to the author, right? So whenever the author bio is updated in the author item, it will be updated in the book as well. Now, if we would add an additional functionality, so we would add a new classics top 10 with the best selling classics, and that would also contain a reference to the book, you could say that whenever the book is updated, we want to update the classics top 10 as well. Now, the effect on our architecture, on our solution, would be this. If we want to update the book, so now the book has an excerpt, this is a new Lambda function, and it of course modifies an item in DynamoDB that generates an event. It's put on the EventBridge message bus, and this triggers the post-process update book call. So now we're fetching all of the items by classic top 10, and if the book matches the book that was just updated, we will update the excerpt in the classics top 10 as well. But this has a really cool side effect in which events start to loop. So for example, when you update the author in this system, it will create an event in DynamoDB, and that will trigger the post-process update author Lambda. Now that Lambda will update the book. So that's this line, the book will be updated. Because that update book will create an event in DynamoDB that itself will generate a new event in the stream, and that can trigger another Lambda function, one that responds to whenever a book is updated. And that can then update the classics top 10. So now you get a single responsibility. You do the update author, and this Lambda function only does that in DynamoDB. And that change propagates over all of the different rows so that you don't need to maintain all that data. And this Lambda function does not need to know about any of the duplication in the system. So now every function has a clearly bounded scope. This is a really powerful solution where this Lambda only does the update author, this Lambda only puts events on the message stream, and this Lambda only responds to updated authors, this Lambda only responds to updated books. And if you want to extend this architecture, that's also easy. So if we would say, hey, we don't only have a classics top 10, but we also have a best sold top 10, we only need to update this function that whenever a book has been updated, we don't only update the classics top 10, but now we also update the best-selling top 10. So because the responsibilities are so clear, you only need to change your code in a single place whenever you're extending your architecture. Now, DynamoDB streams are not always the best solution. They work very well in an environment where you have a low amount of writes and a high amount of reads. But if you have a use case where there are many writes on your DynamoDB table and there might be a low amount of post-processing happening on your mutations, then DynamoDB streams might actually not be your best solution because you're triggering a lot of Lambda functions or a lot of data in your Kinesis data streams that are actually not being used. And in those cases, it might be better to move that responsibility back to the originating Lambda before DynamoDB and not use DynamoDB streams at all. And that leads us to the conclusion. So we've discussed how the design principles for event-driven architecture state that every function should have as few responsibilities as possible, and that we should use services instead of code wherever possible as well. With DynamoDB Streams, we can turn any mutation into an event, and that event can then be processed further downstream by other systems. And this leads us to design very small functions with very limited responsibilities and very short execution times. And this in turn leads to more extensible solutions, higher scalability, and better fault tolerance. When used right, DynamoDB Streams can turn your entire architecture into an event-driven powerhouse. And that's it for this session. Thanks for watching, and if you have any questions or remarks, reach out to me on Twitter.